So we are looking at the buyback delegate contract. High level, the point of this contract is to intercept payments coming into a treasury and determining if that payment should be routed to the treasury and should mint project tokens in return, which is the normal Juicebox behavior since V1, or if that token pair, meaning that the token the treasury accepts and the token the treasury issues back out, if there exists a Uniswap pool for that token pair, to first check if the price in that pool is better than the issuance price, and if so, route the incoming payment to the AMM instead of accepting it into the treasury. That way, the paying person or account, be it from fees or from just clicking the button, will get the best token rate for their payment, and the treasury will forego revenue or new funds, or however they're interpreting it, in the context of there's someone else willing to offer the token for cheaper. It's solved via the delegate infrastructure, which we've been talking about at length this week. So the hooks should be fairly familiar, but we'll go through a little bit at a time and explain what's going on. On the call, it's me, Jango, there's DrGorilla, who authored the contract, kind of lead author, and then Viraz, who helped with tests and with touch-ups and with just giving feedback along the way. So programming heavy crowd, so we might dive a little too deep for some folks, but bear with us and let's see if we can make sense of what's going on. So this contract is the JBX Buyback Delegate, meaning it's designed specifically to work with the JuiceboxDAO project, which issues JBX. This is still the case, right? We didn't change that. Do y'all know, top of your head, if we change that? Pretty sure it's still just JBX specific.
No, because we are testing for project token, so we could use any. But you need to use ETH on the other side.
You have to use ETH on the other side. Great. So it works for payments coming in. So maybe a small note is JBX, kind of as a name title here, maybe is deceiving, and that also might be the case here as well. It kind of suggests the reciprocal token is JBX. We're also making some small refinements as we talk out loud here for things that might need to change before we deploy. So that's a readability, maybe nudge. It's ownable, meaning there's some functions that are administratable. We'll talk about those. It's a funding cycle data source, meaning it gives information to the pay and redeem processes of the Juicebox terminal. It's a pay delegate, meaning it intercepts or it adds functionality into the pay function. And it's a Uniswap swap callback, meaning as it executes a trade, there's a chunk of code in here that'll be specific to that trade environment within the Uniswap contract execution. So it's very heavily dependent on Juicebox protocol and Uniswap protocol.
Just a detail, the callback is mandatory when you're swapping directly with the Uniswap pool. You need to have the callback implemented because that's where you are paying back the pool, the token that you own it. That's why we need to use it.
Yeah. So we'll go into specifics of what that means when we get to that chunk of code. Sweet. So you're going to construct the buyback delegate with the project token that your treasury issues. So the contract needs to have a reference to that token. In this case, in the context of JuiceboxDAO, this would be the JBX token address. It's got to have a reference to wrapped ETH. It's got to have a reference to the pool. And can the pool be the zero address here? Can this be generated dynamically, or do we have to know it ahead of time?
You need to know it. You can compute it since Uniswap pools are using Create 2, but you need to know it because it's immutable. Everyone.
Gotcha. So it's a function of the two tokens being traded and some fee parameters, but you need to pass this in. Cool. I wonder if you can compute this, given that we should know everything in line here. Or maybe we don't, I'm not sure. Seconds ago, can you explain what these Uniswap parameters that we're having to specify are?
Yeah, sure. So seconds ago, it's basically when the frontend is not giving a quote. So it's basically the swap is going to be done by itself. We use what it's a time-weighted average price. It's just we look back in time and we take the mean price across that time. Let's say across the last hour, the mean price is X. Seconds ago is that how long back in time we are looking at. The first one, and setTwapDelta, is just since it's a mean price, will never be exactly there. It's basically a threshold, like a deviation that you accept. It can be at 5% more or less than the mean price without reverting.
Gotcha. So both of these help determine what the allowed price of the pool is once that payment comes in, and the contract is trying to interpret whether it should mint or swap. Yeah, I wonder. Do you have an answer for the question I asked earlier about deriving the pool address dynamically here? Do you think that's possible?
Yeah, sure. Yeah. Uniswap pools are based on create two, so you can do it easily.
Might be cool to have just one less thing to have to know up front. And then you need a reference to the JBX terminal that you're using and the Juicebox controller you're using. So both of these, and this is another note that we should probably have the same prefixes here since they reference the same environment. So this buyback delegate is going to be strongly dependent on a particular terminal version that you pass in and a particular controller that you pass in. So that's all you need to generate an instance of this delegate. And then once you have the address, once you've deployed this contract, you're going to plug it into the funding cycle of the project you wish to intercept that payment and make this decision from. And that project needs to match these, it needs to be operating with this terminal. So it'll only accept payments coming from this terminal. If you're a project that has multiple terminals, payments into a terminal not being this one will break. So there might be a future version that's more accepting of various terminals, but for now this is strongly dependent. And the project needs to be operating on this controller as well. Cool. So now we get to the standard pay delegate hooks. In this case, it's we start with the data source. So remember, the data source is the bit of code that runs before, well, as the Juicebox projects receives a payment, the terminal in which the payment is being processed is going to make a call to the pay data source to ask for some data that it needs to start operating from, like how many tokens should it issue, and whether or not it should call any delegate hooks after the payment has successfully processed. In this case, a lot of the magic happens in the payParams, since this is where the data source will tell the terminal, hey, you should actually not mint any tokens, and instead you should just call this delegate hook where the swap will be made, or it'll say, hey, you know what, go ahead and mint tokens and don't worry about calling the delegate since you, in fact, have the best price in the issuance routine. So we'll skim through it line by line, try to make sense of it. It's a fairly short contract overall, so if we do it line by line, we should still get away with getting out of here by the top of the hour. So the first thing we want to do is find an idea of how many tokens would be minted in the regular Juicebox process, and this is a function of how much is being paid in and what is the current weight of the project's funding cycle. So it's a simple multiplication, and this will give us the standard token count. And then we're going to determine if we were to go with the swap route, how much tokens would I get from that swap. And the way we do this is we first see if the metadata being passed in from the payer. So from the client side, from the person initiating the payment, they can send metadata, and that metadata can include an expected quote, which is the price that we expect the transfer to go, the swap to have, and then the amount of slippage accepted from that swap. So this can be specified from a website or from Etherscan or wherever you're initiating the payment from. You have the option to do that, or if you don't do that, then there's going to be a quote auto-generated given the kind of weighted average price that I think is influenced by those constructor parameters. Correct me if I'm wrong.
Yeah, correct.
Cool. So then this is pretty straightforward. We need a reference to both the how many tokens we would issue and how many tokens we would swap for. So then we can compare. And the comparison is pretty straightforward. If there are fewer tokens issued than we would swap for, then we want to go with the swap route. Otherwise, in this else condition here, which is just kind of what's left over, we want to mint. So in here, we'll specify the delegate as this. So we want to make a callback to this contract, the didPay hook here. We want to send the full amount of the payment. So don't take any of the payment into the treasury and instead forward it to the delegate, because the delegate will need it to swap with. And then also send the delegate some metadata, tell it the expected kind of variables that we had just computed here, which it'll need to make sure that the reserve tokens are distributed correctly and that it knows like what these quotes were. It's not going to recompute those quotes. It's going to use the same information that the data source used up here. Importantly, it's going to send 0 as the amount of tokens to issue back to the payment terminal, and it'll send the delegate allocation so the payment terminal can call those hooks. Otherwise, we're going to send the regular stuff, right, which is the data weight, which is the amount of tokens to issue, and data memo. Again, data is passed into payParams from the terminal, so it's the standard stuff, which the payParams can manipulate accordingly and do some custom stuff with. But in this case, we want to just return all the default stuff. And delegate allocations here is an empty array, so we don't need any delegate callbacks here. Cool. So next function that we have in the delegate here is the didPay hook. So right here, we send back to the terminal. The terminal is going to do its usual business. And then if it may or may not receive this didPay hook, depending on what route it took here. If it did, it's going to make the assumption that it should mint, or rather, it should swap from the Uniswap pool. We're going to need to first start with some authorization here, because we don't want this to be public. If it were public, then anyone could call didPay as if a payment were coming through, and we don't want that. We want this to only come from the terminal that we initialize this contract from, the terminal that we trust. We're going to first parse out the token count swap min amount out and reserved rate that was passed in up here to the delegate. So we have some context as to what we expect to do. And then we're going to try swapping. This is the one thing this function has to do is try swapping. So we'll go into the swap function in a bit, and we'll pass in data, which again the terminal passes to didPay, which is a bunch of context as to what's going on, like who's paying, who should receive tokens, how much is being paid, etc. We're going to pass in the expected min amount out. So the way these trades work is you need to specify the minimum amount you expect out. There's a chance the pool could work in your favor and you can actually get more than that, but you need to specify the minimum because you for sure don't want less than that. And then we're going to specify or send in the reserved rate. Because in Juicebox, when you receive the payment and you mint tokens out, some of those tokens might be reserved for accounts listed on the reserved list. And so once you've executed the trade, you might need to route some of those tokens back to the payer, and then some of those tokens into the reserved list pool. So the swap function will handle that for us. Here we'll keep a reference to the result of swap, which is the amount received. So I think it's guaranteed greater than the min, but it might be more than the min, and importantly, it might be 0, which would suggest the swap failed. And if the swap did fail, then we want to revert to the mint condition, which is the original thing we wanted to do if the mint price was better than the swap price. So if the swap ends up failing for whatever reason, maybe the pool, the price has moved too much, or there's some condition not met that we expected, then we'll just go ahead and mint as usual. And here's just some cleanup. That's very, very edge case, but there might, depending on the state the pool is in, when we try to swap, there might be a case where some ETH is left in this contract from receiving funds in this didPay interaction. So remember here when we tell the data source that we need to go to the didPay hook of this delegate, we're going to send the full payment value. So when we call didPay, we expect this contract to hold the full payment value. And if there's anything left over here, we just want to keep track of it to allow the payer to be able to withdraw it whenever they want. Again, this should just be crumbs. But alas, we don't want funds stuck here forever. So I think first we'll hop into swap, but I'll await some confirmation that this makes some sense to folks. Sound good?
Sounds good.
Okie dokie. Let's go to swap. Swap down here is an internal function, meaning it only gets called, I think it only gets called from that place that we referenced it from above. And here we get to some nitty-gritty Uniswap APIs. So the first thing we're going to do is we're going to try the swap. So the pool here is the address that was passed into the constructor, which is a reference to the Uniswap pool that we're swapping from. I suppose we currently don't have a check if the pool in fact reflects the two tokens that were passed in, or maybe it's somewhere else. But in general, we're assuming the pool is of the tokens we expect. And then we're going to try to swap and give any resulting tokens to this contract to manage. And here's some kind of nitty-gritty Uniswap stuff. Maybe Dr. G, you want to talk through what's going on here? But I think for the general onlookers, this isn't too relevant.
Basically, the summary of this is just ask the pool to swap in one direction, so from ETH to a project token, and then use some kind of price protection to not overpay for stuff. That's basically what those lines are doing. We are just bypassing the price protection, the squared price limit x96, because we are checking it later on. That's, really details.
Gotcha. Cool. So basically bypass because we're going to do some of the checking later on, but it's required and some of it's useful. So if it's successful, if the swap is successful, then we want to take note of the amount we received. So how much did recipient receive from the swap? Does the swap here send funds, or does that get called in the callback hook?
No, it's in the swap main function that it's sent to the delegate contract in that direction. And then in the callback, it's the fund leaving the delegate to the pool, which is done.
Cool. So in the middle of this call, this contract will expect the execution of this function, which is the Uniswap swap callback. So I'll go through this in a bit, but we're going to assume the swap either failed or succeeded here so we can wrap up what happens in the swap call. either we're setting the amount received or we are returning the amount received, which is 0. It's implied to be 0 because it's defined here but never set. And so if swap returns 0, then it's going to assume swap failed and it'll mint instead. But let's keep going, assuming success and assuming amount received is now set. Now we need to do the reserved token dance. And this part is a little clever, but maybe it makes sense if you think about it. So the first thing is we need to compute how many non-reserved tokens we expect to keep out of the amount received, which is the amount received times the difference between the reserved rate and the maximum, so like that percentage difference. And then the reserved is obviously the reverse of that. Yeah, maybe it's worth specifying reserved tokens as the muldiv so that we can just get rid of this. And then non-reserved as the subtraction. But either way, we won't need a reference to both of these. And then, so if there is non-reserved tokens, right? So if the payer is expected to receive some tokens in return, go ahead and transfer those tokens to them. And then if there is reserved tokens, then what we need to do is we're going to mint. We're going to go to the JBX controller, and this is the slightly heady bit. So we're going to go to the JBX controller, and we're going to mint new tokens. We're actually going to mint the same amount of tokens as we just received from the swap. In so doing, we're going to, since we're using the reserved rate here, we're minting new tokens, and some of it is going to be added to the reserved rate calculation. We're also going to set the beneficiary of these new tokens to be this contract. So we've minted new tokens. Now the reserved rate has some tokens distributed to it, and this contract has a bunch of extra tokens. And so now we just need to go ahead and burn the tokens that this contract has that are extra, which is also the amount received here. So I'll repeat that so we can go through once more. The first thing we're going to do is, if there's no reserved, if there are non-reserved tokens, if we need to send tokens out to the payer, go ahead and send that amount over. And this is just going to leave us with the need to reserve tokens. But since we can't just route tokens to everyone on the reserved list here, we're instead going to increment the reserved token ticker so that someone can go in and distribute reserved tokens later on. We're going to do that by arbitrarily going in and minting new tokens. Since we're minting the full amount received, we expect the reserved tokens to be correct. And then we're going to burn the tokens that we received that were extra. Sound good?
Yeah, maybe I will draw something just to explain that.
Yeah.
Mint burn, which is a bit, just an Excali draw or something.
The reason we're minting amount received here and then also burning amount received here, since amount received here includes the amount sent to this contract as well as the amount reserved. So this contract actually, since we were reserving some of it, this contract doesn't have the full amount received from this mint. And so what we're burning here is both the portion of this transaction that we received here, as well as the remaining portion of the swap that we didn't send to the payer in this case, which also equals amount received. So it's probably worth a little diagram to just do the math and make sure that kind of that folks can kind of see the directions things are moving. But we just need these two transactions to fulfill all parties. Next up that is interesting is the actual swap bit here. So what causes the swap to succeed and what causes it to fail? And this happens in this callback function here. First thing we'll do is make sure that this is being called from the pool, since it's a callback from Uniswap. We're going to unpack some data that Uniswap sends us. Mainly, we just want to know what's the minimum amount we are expected to receive. We need to calculate how much of our funds, so the amount being paid in by the payer to a Juicebox project, are we going to send to the pool to execute the swap from, and how much are we expecting to get in return? The two things we need, and I think actually data here we pass in, right? So this is this is what we pass in
in the swap call
right here. Yeah. So we're specifying what's the minimum we expect to receive, and we just want to double check that Uniswap agrees that we will receive this amount. And if not, we're going to revert, which means go ahead and go with the mint case, and let's exit out of the swap case altogether. Otherwise, we're going to go ahead and give the pool all the resources it needs to execute the swap. In this case, it's wrapping the ETH into wrapped ETH and then transferring the wrapped ETH to the pool. And with that, I think we have the bulk of the main cases covered, which is the swap case and the mint case. And the really cool thing, in my opinion, is the fact that even in the swap case, we still maintain the reserved rate issuance. So the reserved recipients also receive the best rate possible. The mint case here is pretty straightforward. Go to the token, go to the Juicebox controller and go ahead and mint. And if mint here gets called again when the swap fails, right? So right here, let's try to swap. If swap returns 0, then go ahead and mint. Since this contract has the full payment, we're going to add that back to the project's balance, and then just emit an event. So mint the tokens, add the funds back to the project's balance, and then it's as if the delegate never got called. So any questions or curiosities about the swap mechanic?
So if someone is paying a project and it's not possible to swap on Uniswap for a better rate, is the user going to be paying more or less gas as a result of a delegate like this being used by a project, or will it have no effect on the gas for the end user?
The user will certainly pay more gas. There's not anything being written into the blockchain's state, which are the big kind of gas guzzling transactions. So there's a few more lookups and reads involved. Like the terminal has to make a call into the data source and the delegate contracts. So the baseline gas or paying into whatever project uses this buyback delegate will be slightly higher, but it'll only be significantly higher, maybe twice as high, if the swap case does take effect. And the swap case should also then be compensated enough, right? So like you're paying more gas, but you're also getting a lot more in exchange. You're getting a much fairer JBX or whatever project quote than you would otherwise. It's a good question, though.
Okay, makes sense. Thank you.
Okie dokie. Yeah, this is definitely the thing to wrap your head around, to kind of get the maths straight. Especially this burn amount here and the fact that these are both amount received. But once that makes sense, then we're good to go. So that leaves us with a few smaller functions. The first one is getQuote, which this is the quote that is generated if the client does not pass in a quote themselves. So remember in the payParams data source hook, the client can pass in a quote that it expects. So it can choose the slippage it wants, it's comfortable with, and the quote it expects. But if it doesn't, then we're going to try to get quote as an average over time. And this is that calculation. It uses the setTwapDelta and the secondsAgo that we mentioned from the constructor to give us some threshold of prices that we're comfortable with. That's the one place this is used. We have the sweep function, which allows anyone to reclaim any leftover funds in this contract from any kind of edge case pool inefficiencies that leave some ETH in this contract here. Very edge case that you'll need to use this, but it just ensures that like the small leftover bits of ETH don't get stuck in the case of a very shallow swap pool. And then we have a few admin functions. We have increaseSecondsAgo and setTwapDelta. And these are both just conveniences, so an administrator can tune what are appropriate auto quotes that the contract should look for if not passed in directly. These should probably stabilize over time, but they're certainly a function of how deep the Uniswap pool is. The values might become more conservative as it becomes harder to manipulate a pool as it grows in size. But in the beginning, these values should probably be a little bit more flexible to account for the various unknown ways in which a pool's size can change. Since these are all decentralized and anyone can add liquidity to those and remove liquidity from those.
Just that's a detail, but the seconds ago, the time frame across which we can get a TWAP depends on the pool itself. You need to initialize a pool and you need to update some kind of state to allow bigger time frame. That's something that needs to be proactively done. That's why we have that function as well, is that maybe at some point you just realize that the time frame that you're using is too short, too small, and can be too easily manipulable, and then you want to increase that, but you need project owner that needs to increase it in the pool itself and then call this increaseSecondsAgo as well.
So you need two transactions here. You need to first, is the pool, is it ownable too? The pool itself? So you're saying the
No.
owner of that pool needs to change
No,
a value?
anyone can do it. Anyone can. It's called increasing the cardinality, and anyone can increase the cardinality of a Uniswap pool, but you need to pay for gas, and it can be quite expensive at some point when you have super huge cardinality, like
Gotcha.
a few days or so. We don't need that. But that's something which can be done.
So these are administratable functions that if you are thinking about applying a buyback delegate to your project, you should probably be aware of how your pool is set up and how you might use these two to tune. But again, clients making payments into your project can bypass them by sending their own quotes. The price you get from the pool is depending on these values, but anyone executing this trade by paying into your project can also specify the values they're comfortable with. So these are just default values in case you have some more automated process making payments into your project, like JBDAO does. JuiceboxDAO takes in fees as projects distribute payments. So there's no opportunity during those fee distributions to pass in quotes. So we need to tune the JBX pool values here. And that's it. That's the contract. This is just a necessary redeemParams data source hook for redemptions. It's just going to pass in all the standard empty values. And I think that's it. We have a few storage properties to keep track of things as we are fulfilling our commitments to project payers. And we emit some events along the way and throw some errors along the way too. But that's the buyback delegate. A very fun little project that ends up being little despite it being a very delicate process. And the good news is we've managed to get it littler over time with really kind of reasoning about how some of these things play together. But I'm very excited to use this in JuiceboxDAO and several other projects because it really improves the efficiency of how tokens get distributed. And I think a large component of these networks is efficient token distribution and broad token distribution. I know it's been a big topic in JuiceboxDAO, both from the pay side as well as from the reserved rate side. So something like this is likely going to be worth the trade-off of the incremental gas that it'll cost to attach, but we'll have to see in practice how it feels, and I'm excited for it. Thanks for leading the way, Dr. G. Thanks for all the help, Viraz. And thanks for the nice pointed question, Matthew. Nice. Anything else to cover here?
I had one question. Let's say the project's issuance and the market rate are close, but the market rate is better, and it tries to swap on Uniswap, and you end up getting sandwiched. Is there like a chance for the end user to actually get fewer tokens by going through that swap, or is that just like a pretty far, like an edge case?
That's why you have two securities for that. I mean, really, any end user, as they have like manual control on the data that they are passing to the pay function, should really pass a quote, because you cannot get sandwiched then. That's really the ideal protection, and that's why we have a TWAP as a fallback security to avoid, again, getting sandwiched. Because if you have too much of a deviation to that mean price, then that means that either the pool has been manipulated, which is perhaps not the most likely case, or you're just in the middle of a sandwich, and that you want to avoid, of course.
Yeah, the one thing to add is there's also a case where, let me find the right chunk here. In the payParams, once we know what the issuance would be, or the expected swap would be, and we're comparing here, there might be a benefit to leaving a difference here. So like tokenCount is less than swap amount plus a margin. Depending on the amount of JBX you are getting, oftentimes these fee payments are fairly small. Leaving a difference between what the swap would be versus the tokenCount might be beneficial from a gas perspective. Like you pay less gas, just mint, because I'm getting 10 JBX if I mint and 11 if I swap. But with the extra gas, I could have gone and bought 2 JBX or whatever, right? So there might be like a benefit in the coming days here as we're just doing final cleanup to articulate a small difference here. But mostly it's just taken into consideration, as Dr. G said, with the quotes that you're passing in. So it's the burden is kind of left to the clients in most cases, and the TWAP should work itself out in the majority of cases. But it's hard on the margins. It's hard to find the right guaranteed optimizations on the margins, especially with small values.
Yeah, but that's just having a higher slippage, actually. So you can already do it now. If you're just concerned that it's really too close to what you would get by minting, you just increase the margin. By increasing it, you're just saying the minimum amount received by the swap should be even bigger than before, and there should be a bigger difference with the token count, which would be minted.
Nice. Yeah, makes sense. Yeah, I guess there's like the theoretic possibility of artificially keeping a delta here too. It's kind of like you're to play the game of, all right, you pay a fee in and you have the same price that you can then go and re-exchange the tokens for your fee back on the market. Obviously it's another transaction, you're paying the gas, but there could be a spread that like, okay, we're willing, like the buyback delegate will go and get as much tokens as it can, but it'll also mint instead of swapping if there's a delta, to kind of create a little bit of a difference that if once you do the swap and if you go and re-exchange immediately, then you will get most of your fee back, but you still have a little delta of that fee paid in. Again, this is usually just taken care of in the market. Like the price will swing around and you never really know what you're going to get. But I think in this operation here, there might be room for creativity for folks who want to take this contract and run with it to kind of do some dynamic or kind of interesting things that kind of treat this comparison slightly differently. But in general, yeah, once you're interacting with the Uniswap or the AMM, you're opening ourselves up to some chaos, and the contract does what it can do to keep the chaos bounded. You can't get rid of it entirely, but you can revert if it's too much and then go with the default case.
Is there any plan for this to be exposed in the front end in some way? Like, is someone paying a project and, if it does happen to use the delegate to swap and they get more tokens, like, are they going to be aware of the fact that this occurred? And also, I guess, secondary question would be, we'd be able to see in the front end, like, oh, this project is using a delegate of this type. Like Juicebox, for example, is using the buyback delegate. Like, will the end user be able to see that?
So from a contracts perspective, yes, that information will be available. The address of a buyback delegate will be knowable, and you'll be able to look at a project's funding cycle and see if it has a knowable buyback delegate attached. And once it knows that, it can make calls willingly to payParams. The front end can go and get what the payParams would be, which is the same payParams that the terminal is going to ask for once it starts execution. And the payParams that'll be returned are one of these. So in the case that 0 is returned and delegate allocations with this metadata, then the client will also know, hey, sweet, I'm expected to get this swap amount out. And it can show the user, and when it's making a payment, then it can tune the quote and slippage as it wants. You can do that ahead of time too. So if the client calls payParams, it can send the data that it expects the terminal to send with. In the data, it can send the quote and slippage. So you can have a lever in the front end that has a very Uniswap-like quote and slippage parameters. So the client can make a choice. But yeah, it's definitely going to take like a sprint on the front end to have the visuals in place in a sensible way. I'm sure we'll have to navigate the complexity conversation too, because all this stuff, it does add value in certain ways, but it does add complexity or cost, right? So if you want to avoid complexity in the front end, you're going to pass on gas costs. So there's definitely that conversation to be had, but the contract exposes the ability for the front end to do all that. First step is kind of get this in place, and then I think these upcoming weeks is a perfect time to figure out how this fits into the priority queue of a front end. The biggest benefit for JBDAO here is going to be on the fee side. As projects pay fees, it'll auto go through all this process. So there's no front end for that. That'll kind of just be baked into the distribute payouts transactions that everyone else and JBDAO itself triggers. But if you were to go and just click pay at the JuiceboxDAO's end, you would be assuming that you will go through this getQuote weighted average price case and not this custom specified quote and slippage case. And likely, if everything is left the same, the front end would quote the mint price, which it's probably calculating, given these same values, and miss the fact that actually that's not what you would get. You would get this swap price if it's better. So it's definitely worth making sure that front ends are aware of what's going on and that we have an available spec for them to reference and build from. Any other questions? We have a few inspirations for some small touch-ups here at the end, but let's look forward to getting this out the door in the next coming days. Thanks, y'all.